Okay, so first I want to thank the organizer for inviting me in this conference. So my talk will have two parts. The first part is on the topological Wigner crystal in pattern layer graphy, but the work is really done by my student Moiré and my postdoc Yahui Zhang. But apparently there are so many talks on this topic, so I will try to move faster, and hopefully I will have a time for the second part, which is on fractional quantum spin Hall related to twisted MOT2. Okay, so I guess I can skip the introduction. We all know, the breakthroughs in these two experimental systems. The first part were on the pattern layer graphy by Longju. So actually, we already anticipated, this kind of ABC stacked graphy system aligned with HBN is a wonderful platform for, quantum Hall physics, quantum nonce Hall physics. Together with Center, I think 6 years ago, we already pointed out you can find a nearly flat chain band. So in this paper, we calculated it only for bilayer, the tri layer. So we found that there are two sides. One is the trivial side, one is the topological side, depending on your electric field. And for the topological side, the chain number is always equal to the number of layers. And it's very easy to explain this. And following this theoretical prediction, I think Feng Wang has a nice experiment in the ABC tri-layer graphy. He shows that indeed in the topological side, topological side means the particle is moving away from the HB. There is a chain insulator, but the chain number here is actually 2. It's not a 3. Now 3 is the predicted value. So I was honored to be a co-author of that experimental paper. So we found, the resolution is, we really need to take care of the interaction effects, because if you only calculate it in the single particle level, the band gap is actually quite small. So if you include the interaction it can modify the chain number. So this is actually the first example we know, in this kind of system, interaction is really important. Of course, now we know there is an even more extreme example, the 5-layer system by Longju. So I will skip the experiment. Okay, so in this case, there is an even bigger puzzle, right? So if you follow the logic in our old paper, the chain number should be 5. But of course, we know, interaction is important. But in this case, interaction is not just modify the chain number. Because Long's experiment is in the regime that the displacement field is so large, so we can do some simple estimation. We can project the Moiré potential to the conduction band. And we found that the Moiré potential is only around 0.1 MeV. It's really like a perturbation. So it means the interaction is not just modifying the chain band, it's actually maybe the source of the chain band. So we did this Hartree-Fock using exactly the same method as Ashwin and the Center. Our papers are posted at the same time. So that's very easy, right? So, in the left side, you see this plot. This is single particle calculation. It's just a math. Then you do Hartree-Fock, you find a narrow chain band. And in this plot, we show two lines. One is solid line, one is dashed line. They corresponding to whether you have or turn off the Moiré potential. You cannot see two lines because they are basically the same. So it means, the Moiré potential here, at least in this calculation, it does not play any role. So this state actually breaks the translation symmetry spontaneously within this calculation. Okay, so as Ashwin said, we should interpret this as a topological version of a Wigner crystal. Everyone is saying the name nonce Hall crystal, so I will also use this name. So when we found, so this is the density profile before the Hartree-Fock. You can see it's basically uniform because Moiré is weak. But once you include the Hartree-Fock, you find that you spontaneously generated this crystal. So actually, I have one minor issue which I don't agree with Ashwin. So I think, so for most of the region, we indeed found that C equal to 1 is a honeycomb lattice. But for some other parameter regime, we found, the density profile is triangular lattice. Naively, you would think it's a trivial Wigner crystal, but we found the chain number is still 1. Okay, it's just a minor issue. So this is a phase diagram of chain number. In terms of the displacement field and the twist angle decides the Moiré period. So I wanted to point out, for some twist angles, there is a transition from C equal to 0 to C equal to 1 tilted by displaced field. Okay, so in my calculation, so this regime, so this is C equal to 1, this is C equal to 0, this is C equal to 1. You increase the displaced field, there is a transition. Okay, so we also did some ED, right? So our ED is following a very naive, crude approximation. So we assume, when we dope holes, the band does not change. So my understanding is, this is just some kind of Born-Oppenheimer approximation. I assume the crystal, this spontaneous crystal, is just frozen, and we just, just calculate Hamiltonian form electrons. It's kind of naive, but this is what we can do, so we just did it. And if you follow this assumption, obviously you will find the FCR, right? There is a flat band. You go to fractional filling, it's quite obvious, so I will not emphasize that. So here is some new results, as some preliminary results. So I heard from Long, he found this extended quantum norms Hall crystal and fractional filling. My collaborator Matt also told me he has another sample which shows integer quantum Hall effect and 2/3 filling. So here I'm trying to study the competition between fraction and integer states and this filling 2/3. So we are targeting these 3 different states. Let me explain. So the first one is just FCR. So you assume you have the same crystal as the nu equal to 1. You dope holes form FCR. The second one, I call it crystal 1. This one is just means your crystal period is just locked to your density. So you just can fill one band. Okay, so it's the same state as the state at nu equal to 1, which Ashwin and I just talked about. But now we just assume at the filling 2/3, it still happens. Now there is another state, I will call it crystal 2. So crystal 2 has an even larger period. In this case, you will fill 2 bands. Okay, so these 3 states are completely different. They live in different corners of Hilbert space. So the basic thing we can do is, we target the ansatz within each sector and compare their energies. So this is a plot. So for these 3 states, and you can see their energy are basically very close. I don't know why, but they are close. So the energy difference is below 0.5 MeV per Moiré unit cell. So this means, I don't think I can trust this calculation because, what we did is an approximation. I don't think, I can trust the calculation can give me a very precise energy, and to the order 0.5 MeV. So the only thing I can say is there are really some competition between several different states. Okay. So this plot shows the energy difference of crystal 2 compared to crystal 1. And we found, in the larger displaced field, crystal 2 actually may be favored. Again, within this calculation, I'm not sure this is correct or not. Okay, but at least it's a strong candidate, it seems. So let me explain this crystal 2 because it's a new state. So I targeted this state because there is a trivial explanation of the extended quantum norms Hall phase. Basically, you start from nu equal to 1, you add holes. Holes form a trivial Wigner crystal. So this crystal 2 exactly has the same symmetry. So it's allowed in the Hartree-Fock calculation. So we were just trying to target this trivial explanation. But surprisingly, what we found is not the trivial Wigner crystal of holes. So this state, we believe it's a new state, so in the Hartree-Fock calculation. So we can find that trivial state, but we didn't find that. Okay. So this state, you have the density profile like this. You can do a Fourier transform. There are 2 components. You will find that the component that corresponds to nu equal to 1 is actually quite small. It's dominated by component at nu equal to 1/3. So it's not a reentrant state of nu equal to 1. I think, personally, I think it's really a new anomalous Hall crystal. I will call it anomalous Hall crystal 2, because in this state you have 2 bands filled, and their total chain number is 1. Okay. So this is a summary of the first part. So I think, I just wanted to say, we have an interaction-driven topological Wigner crystal, as Ashwin already said. So the new thing is here, I found there are really some close competition between these several different states with different crystal periods. I don't think our current method can really tell us, which one has lower energy. We need better methods. And then, I want to emphasize this anomalous Hall crystal tool may be a good candidate for this experiment, but we don't know, right? We need future experiments to really decide. Okay, now let me move to the second part. It's motivated by the Cornell group experiment on the fraction quantum spin Hall in twisted MOT2. Xiaodong already mentioned it this morning, so I will not speak too much about the experiment. So basically, in this experiment, at this 2.1 degree, they found quantum spin Hall effects and filling 2 and 4. That's expected. But the surprise is, it seems RXY is 0 and filling 3. That's quite a surprise. Because usually at all the integer filling, we expect the value is fully polarized. But here they didn't find that. Instead, they found a fraction quantum spin Hall effect. The evidence is really from two-edge conductance. Okay, so I understand the experimental situation of this is not very clear. So here I will just talk about the theory. Okay. So if you assume this state is, I cannot claim anything about the experiment. So if you assume this state, I think the basic picture is clear. So for each value, you have these Chen bands, and we definitely just fully fill the first Chen band for 2 values. Then you can just look at the second Chen band, and for each value, just half filled. Okay. We don't understand why value is not polarized, but let me assume value is not polarized. So it's half plus half from the experiment. Now we ask, what kind of states we have, which is consistent with the fraction quantum spin Hall effect. There is one obvious answer, everyone knows. It's just a decoupled phase, right? You have a quantum Hall in one value, another quantum Hall in the other value. It's so obvious. So the question I ask here, it's a purely conceptual question. Is there any other non-trivial candidate which can give you this effect, but it's not a decoupled phase? Okay. So I'm not trying to study any concrete models. I don't think I can make any claim about the experiment. So I'm just trying to answer this theoretical question. And I think it's meaningful regardless of the experiments. And I will show you, the answer is yes, because I can provide one concrete example. Okay, so here is my logic. It's from this. So these 2 papers are really the same paper. I already had the series 6 years ago, but never published. The experiment really gives me a motivation to publish it. Okay. Yeah. Here is my thinking, right? So we are talking about the half filling plus half filling of 2 Chen bands. So I can make an analog with a famous problem. Ballet quantum Hall, you have half filling plus half filling of 2 London levels. In that case, I think we know the answer very well. It's excited condensation. Because of Coulomb, electron and hole just form exciton and exciton condenses. Okay, so here we can make a similar argument. But here there is a crucial difference, right? Because you can make an analog with London level, but now our case is 2 London levels have opposite chirality. So you can assume you still form exciton because interlayer or intervalue repulsion. But one crucial difference is, in this case, exciton actually fills an effective magnetic flux. So that means, its condensation may be frustrated. So instead, I'm thinking about a state, because of magnetic flux, right? The excited condensation will have a vortex. So this vortex may move. So maybe we will have a vortex liquid of excited. So that's my, that's a hand-waving argument. So the real question is, how do we form a concrete theory of a vortex liquid of excited, right? Because right now this sentence really is meaningless. Okay. So it turned out the best way to form such an exotic state. So we cannot do Hartree-Fock anymore, right? So this is the very interesting physics. So we cannot do Hartree-Fock. So here we found, sorry. Here I found the best way is actually to start from, you want to describe an exotic state. The best way is to start from an exotic state. So I start from an exotic state which everyone agrees. That's the compound firm liquid. Thanks to Humphrey, Lee, and Reed, I think we know that state exists, although it's super exotic. Okay. So I start from the decoupling limit. At half filling plus half filling, obviously there exists a compound firm liquid for each value, right? Because we know, because of the strong correlation, electron will it's not a good language. The good language is compound Fermi, and compound Fermi form Fermi C. So this is the theory in the decoupling limit. So basically, you have two copies of compound Fermi liquid, but they have opposite chiralities. So let me explain this theory. So first, for each value, you have a Fermi surface of compound Fermi coupled to an emergent gauge field. So we have two different emergent gauge field from the two values. I will call it small a plus and small a minus. There is also a probing field, which is a plus and a minus. Okay. So you can do some redefinition just for simplicity. So you can redefine, big AC and big AS, also small AC and small AS. So there is a mutual transformance term between the big A and the small a. So it basically tells you, that in compound Fermi liquid, the charge is not carried by the compound Fermi. It's carried by the internal flux. It's a very exotic property of this space. Okay. So after this reorganization, you find the mutual transformance term is like this: big AS, big AC, small DAS, or big AS, small DAC. So it tells you, if we create an internal flux of small AS, so it means it carries charge in the both values. So that's like a Cooper pair. And now, so this phase is in the decoupling limit. So now we wanted to end the strong inter-value repulsion. So that means we wanted to suppress the same occupation of the two values, right? So it's like a malt insulate. You wanted to suppress the double occupancy. So basically, you wanted to suppress this process. So you wanted to gap out this mode AS. So how do you do that? So I will propose this way. So it turned out, a good way to do that is you add a term which is the exciton of compound Fermi. So I'm basically saying, in this system, maybe what happens is not exciton of electron. It's exciton of compound Fermi. So this exciton of compound Fermi is very easy to understand. You have two Fermi surfaces. Exciton of compound Fermi is just a hybridization between them. After that, two Fermi surfaces just split to, two bands. Okay. If this hybridization is large, you will only have one Fermi surface. So this is one consequence. The other consequence is this internal field AS will be fixed. Okay, so you will only have one internal gauge field, which is small AC. So the final theory will be very simple. It's just like this. So we have one single, so let me assume hybridization is large. So we have one single Fermi surface F couples to one single internal gauge field A plus this some other mutual transformance term. So if you are an expert, you probably will notice the similarity of this theory to Song's Dirac theory of compound Fermi liquid. Actually, this phase should be understood as a CFL compound Fermi liquid of excitons. Okay, so let me explain. So this internal gauge field A is really like a Gold's mode of excitondensation, the RVC order. And this Fermi F, it's neutral. It should be understood as the vortex of the RVC order. So usually, if F is gapped, what you get is just the RVC order. But here, what happens is this vortex of RVC order is proliferated. And these vortices are fermionic, and so they form a Fermi surface. As a result, so locally this space still has exciton, right? But just this exciton does not have long-range coherence, because you have these vortices which can move. So let me summarize, this property of this phase. So first, it's an insulate. It's incompressible in charge channel. Second, it's gapless in spin channel. It's compressible in spin channel. So it means it's a spin liquid. So there are bulk excitation which are gapless and which carries spin. Okay, so this is the second property. It's a spin liquid. The third property is it has a quantized, half quantized quantum spin Hall, fraction quantum spin Hall effect. This also means, there is oscillated helical edge mode despite the bulk is gapless. Okay. Yeah, so it's a very interesting state. It's not a gapped fraction quantum spin Hall insulate. It's a gapless fraction quantum spin Hall insulate. But because what is gapless is neutral, so it does not influence your measurement. So I think it's consistent with the experimental measurement. So to detect this gapless thing, you really need to do thermal transport. So that's very hard, actually. So this is a theory, right? It's very exotic, so I cannot tell you a concrete model which can realize it. But what I can tell you is, how we can distinguish this phase with the conventional decoupled phase of Franklin quantum spin Hall effect. So it turned out, I think the cheapest way, the most direct way is just apply the Zeeman fit. This is because the decoupled phase, it cannot survive to a finite spin polarization, in my understanding. Because you start from the decoupled phase, the sigma xy is 0, simply because the two values have exactly the same electrons, so they can cancel. But once you have a finite spin polarization, two values have different number of electrons, so sigma y is not 0. Okay. So for example, I can show you, this plot. So this is a plot which I really want from the experiment, but they didn't show it in the first paper. So I hope, in future we can see this plot. So if, this candidate is just a decoupled compound firm liquid, then what I'm imagining is, you apply magnetic field, you will generate a spin polarization immediately because CFR is compressible. And after that, this basically your electron and hole doped the two values. And this will generate a sigma xy. I believe it will be proportional to B. If you start from a decoupled fluffy phase, because it's a gapped phase, so I think magnetization will be 0 for a wire until a critical value of Zeeman fit. And this critical value of Zeeman fit, I think, is proportional to the gap. It's like a Pauli limit in superconductor. And after that, the sigma xy will again oscillates. Okay. But the vortex spin liquid is really different. Vortex spin liquid is compatible with a finite spin polarization, so I think it can survive to larger magnetic field. So why is that? Because in vortex spin liquid, we really have spin charge separation. Because as I said, locally electron and hole, they still form exciton. Exciton are neutral. So you generate this spin polarization, you are just dope excitons into the system. Exciton are neutral, so they don't destroy the charge gap. They don't destroy the Franklin quantum spin Hall effect. So the Franklin quantum spin Hall effect will be still just 1/2 as in the zero magnetic field. Actually, I think there may be a possibility that even at zero magnetic field, you spontaneously generate a ferromagnetic moment. Okay. So this, I think, it's not very possible in the decoupled phase, but it's consistent with this more exotic state. So I hope this may be useful for future experiments to verify this state or rule out this state. So let me summarize. So basically here, I'm just propose a theoretical candidate for the Franklin quantum spin Hall insulator and all the integer filling. It's different from the decoupled phase. And it can be compatible with finite magnetization. Okay, so this phase actually has some other descendants. Okay, I don't have time to talk about that, but I can talk more if I have a question on that. Okay, so that's all of my talk, and thank you very much.
Open up for questions.
Can you go back to those energetic comparison you had in the first part of your talk, that slide?
Which one?
You had energetic comparison of your three states, which are almost on top of each other. Yeah. So this situation, of course, is very common in regular quantum Hall effect. If you just calculate the energetics of the charge density of a Wigner crystal state and fractional quantum Hall liquid state, they're almost parallel. So that's why predicting where the transition takes place is very difficult. What stabilizes the fractional quantum Hall, that's a function of nu, there are cusps. Here, of course, you're sitting at a nu. So in fractional quantum Hall also, you'll find the energy difference to be very, very small. Okay, so this is, but the thing is that in Longju's experiment, but this is all a ground state energy competition.
Yes.
This will tell you something about whether there is a ground state quantum phase transition as you vary nu and d. This has no statement about temperature at all.
Yeah.
His experiment is not a ground state phase transition at all, although he calls it a phase transition. It's a crossover. He's seeing things as a function of temperature. He's seeing at a fixed d and a fixed nu, but several different nus. And he finds that at low temperature, he has an integer quantum anomalous Hall effect, or high temperature fractional quantum anomalous effect. This sort of energetic argument will never explain that, because there, unless you claim there is a temperature-induced thermodynamic transition, which of course there isn't, this sort of picture would not explain that. I just want to.
With you, yeah.
Yeah. Do you agree with me?
Yeah, definitely. Yeah. I fully agree with you.
What is the point you're making here? Is that D versus D and nu-driven transition? Is that what you're talking about, which you also sees?
I think the only thing I want to claim here is, we have these states, they are closed in energy.
Oh, you're just saying that.
Yeah, I don't want to make a stronger claim.
I got it.
So because even for ground state, I don't trust this calculation.
No, I just wanted to make sure I understand. I didn't think that you were saying something bad.
No.
But
I agree with you.
Yeah.
I just don't know how to calculate that.
I just want to make sure. Second part of your talk, I do agree the experiments are not easy to understand because they're 8-state transport and probably one second part. Okay. But I am slightly confused. If you have this, if your starting point is 2 half-fill bilayer, which I think I kind of understand, in principle, many, many different phases are possible, as you know, right? If you do the K theory correctly, many possible phases, okay? And then you have to do numerical calculation to see which one has lower energy.
Yes.
So here, I'm just missing something. I know your work a little bit, but I did not pick. How are you picking this composite fermion of excitons, exciton composite fermion, composite exciton liquid, okay? Which I like very much. How are you concluding that is the phase? That's just one possible phase, right?
No, there are many ways. So first, I agree. I don't do any concrete calculation. I cannot say anything about the energetics. Okay, so I'm just trying to talk about the possibility.
Okay.
So there is one possibility is the decoupled phase. I didn't talk about that because it's so obvious. Okay, so I'm just trying to propose another candidate, and this is the one I can.
I agree and accept. But you're saying this is an interesting possibility. What are its properties? Thank you very much.
Yeah.
So going back to your phase diagram with
this one?
Yeah, so it's a bit different than what I just re-looked at your paper. So can you tell me what the difference in parameters is, for example, with the Parker model? Do you remember?
With the what model?
Well, the Parker model.
Oh, you mean
the model used by Parker, yeah.
Oh, I don't know.
But the phase diagram is, for 0.7 is completely different. Probably there's small
I think
gaps
we probably use
different
Hopkins. I think that's T0 maybe. Different.
I guess my point is if there's this universal argument, right, which I agree with, the 3-patch model, even though it's gapless on gamma m, gives you a Berry curvature. So I just want to know what extra parameters influence that.
I really don't know. I didn't study this very carefully.
Should be. Okay, and the second question is related to your fractional state.
Yeah.
So, you're basically doing a fractional calculation, not the previous one. I mean, I made this point many times before, so it's belaboring an obvious point. But there's a calculation that you fractionally fill a band that you obtain at filling nu equals 1. And then you get a fractional Chernus later. Why should I think that's an okay thing to do if the system is gapless in bare physics?
You're talking about this one? Okay.
I'm talking about the
that
one. I mean, I wish I didn't have to ask it, but since you showed it, I have to ask it.
Yeah, I'm about to take that question, but can you repeat it again?
Well, the question is, first of all, you have the charge spectrum there, right? Not even the Goldstone spectrum, right? So the charge spectrum is gapped at filling 1. Yeah. But then you're fractionally filling a state, so you're assuming basically rigid band, and you're fractionally filling. Of course, if I fractionally fill a Chern insulator, I'm going to get a fractional Chern insulator. But your system that you start off with is gapless. So if I start off with, what one should do is start off with the gapless system is filling 1/3. So why should I believe this calculation?
I mean, I think you can ask the same question for the conventional solid state, like twisted MOT2. That state is also gapless.
That has a gap. That has a gap by the Moiré.
Because there are acoustic components.
That's
FCR as defined as fully gapless state does not exist.
You're confusing the issues. There's a single particle gap. No, that's very important, and you're confusing the issues. There's a single particle gap. Here, at nu equals 1, there's a gap given by your interaction. Okay, so your interaction is of the order of the gap anyways. Even if you were to project here, you'd need to take into account more bands if you wanted to not take the original system, which is gapless to start off with. So so I disagree that it's the same situation.
I mean,
you agree? that you agree that what I just said is correct.
I think the only thing I can...
You've got an interaction. Your interaction scale is of the order of the gap. How do you neglect that advance?
I think it's sufficiently nuanced. You guys can take it offline.
Andre is asking, are you agreeing that disagreeing? I think that is what you're asking. I have the questions to the last part about this composite fermion exciton case. Would it be actually easier to realize something like the, again, quantum or bilayer, say graphing quantum or bilayer,
no.
electron half field electron lambda level combined with the half field whole lambda level, such that you totally could. Why is that? Why not?
Because I want a repulsive interaction. And in that case, you will get an attractive interaction.
So okay, that's kind of key.
So the sign of interaction is important.
Okay, sign is important here.
Yeah.
Okay,
so in your case, you will just get a exact condensation. There is no frustration.
Yeah. Okay, great. Thank you.
So, like in the case where you have this exciton, like composite Fermi, like what do we call it? Exciton vortex liquid state, right? You said that you could have a non-zero spin polarization. So, should I just think of them as the excitons getting spin polarized, or?
No. It's just you change the exciton density. Now, spin polarization is just exciton density. Right?
So, but the excitons are forming between the...
Exciton is formed between electron in one valley and the hole in the other valley.
I see, okay.
So you can map it to a spin model, right? So SD is really just the density of exciton.
So it's basically spin valley locking of the opposite values you are using with...
No, I'm not talking about spin valley, right? The spin and valley are the same here. Let's not confuse with the notation. We only have spin up and spin down. They have opposite numbers. Exciton is just...
okay, I see, sorry.
Yeah. Exciton creation operator is just S dagger. Exciton density is just SZ.
Any other? Oh.
The last slide you had, can you say a few more words about how you get all those different phases from your composite Fermi liquid?
Oh, that's so obvious. Yeah, so okay.
You can't believe somebody is asking you this question.
No. I can explain it in one sentence. So in half-field London level, there is a composite Fermi liquid. It's a parent state of all of the other states, right? You get a J sequence, you get a non-abelian state from Perry. So here I'm just doing the same thing, because this state is a composite Fermi liquid of exciton. So you can imagine if you choose the exciton density, you will get a J sequence. If you give a Perry of this composite Fermi liquid, you will get a abelian state or no abelian state, depending on whether it's weak pairing or strong pairing. So if it's strong pairing, it's actually a Z4 state, which was also discussed by Chaoming and Chen Ke. If it's weak pairing, it's a non-abelian state. So I'm just copying, the old story here. Yeah.
But the reason it's different, like you get Z4 compared to the, I don't know, 331 or whatever, is it clear why?
I don't have one sentence to explain that. Yeah.
Is it got to do with the quantum spin Hall part of it?
Yeah, probably. Yeah.
And the Jane sequence you get by tuning the field? Is it
just change the SZ, right? Because SZ is the exciton density.
So magnetic field then, right?
Yeah, so you look at this action, right? The exciton, so change SZ is really change the magnetic flux of DA. Yeah.
Any other questions? All right, let's thank Yahui again. See you tomorrow at 9 a.m.